We are live. I know it's a little late, but Tuesday went by quickly because many people decided to call me today. My family, some friends. And here is Fuji, Baji, and Suji. Actually, you know what? We need to share the live. So I just wanted to say that we were live yesterday, last night, slash very early this morning. And it was really nice. I started to talk on the topic of dark matter. And many of you seemed to really enjoy it. And that was lovely. Oh my gosh. There is a fight breaking out here in the kitchen, potentially. Let me actually go get my laptop really quickly. Hopefully that you see my live. Welcome. If you just joined, thank you for being here. I hope that you can see the live, and I'm about to share it on my channel as well. It takes me a minute to set it up on the other device. But yeah, thank you for being here. We're a little late, but here we are. And last night slash this morning, we had a really good quorum. Let me put you right here. Just 1 second, sorry. Actually, let me put you right here. And go get my laptop. So, I am on the live now. Let's see. Do I see it on my YouTube? So, if you are joining, welcome. If you're seeing this as a video upload later on, then also welcome. Thank you for being here, and as usual, sorry, now I see your view. It's not the most exciting view, but here's a fridge. Here is Baji, and sorry, I'm still sharing the live, so it takes me 1 second here. Oh. There, shared it, and also I'm gonna put it on my channel, so I share it to my channel. Hi, hello, hi, come, pet your cat. Hi, Munchies man. Sorry, there is some laundry lying over here. Should probably remove that. And this is actually stuff that I need to take downstairs to the laundry room. So never mind that. But here is Suji Mama. Here is Suji, and there is Baji, and Fuji is here somewhere. I think Fuji was telling me his opinions today of his for what treats he wants, and now he has gone upstairs. So thank you, everybody. Give me just a second to get everything settled for this live. I still have to share it on the channel. I'm just like sharing the link and everything like that. And we will get started with a very interesting topic today. So yesterday we talked about dark matter and various candidates of dark matter. Hi, Maria. Hello. Hi, Maria Gomez. How are you? Hello, Calm. Hello, Munchies man. Trump. Hello, Trump. Hello to Pet Your Cat. So, Yesterday, thank you so much if you were here yesterday. We had a very nice live. Say, crack my finger. Hello, Trenton Ferris. Say, crack my finger backwards. Hello, Puma Fist. What's up, witches and warlocks? Puma Fist tuning in. Thank you for being here, Puma Fist. Welcome, welcome. We're just getting this live started. Usually our lives last for a long time. I haven't even made my tea yet. So you'll probably see some nice tea boiling, some water boiling, some tea being made, some bubbles forming, some blue lights going on. Hi, Andre, I missed you. How are the kids? The kids are right here. Hi, Sufyan. Hi, John. Hi from San Antonio, Texas. There is a little kitty cat fight going on there. What is this channel about? This channel is about the kitty cat. So we show the kitty cat. Sometimes I show my face if I feel like it. But generally I do the kitty cats and at least my voiceover. And we also talk about physics and various interesting topics. We can also talk about some educational information that you want to share, Puma Fist, if you'd like. But often we talk about a physics topic, and in fact, I've been doing a lot of what is going on here? Suji Baji, Karnashana. I like the way you said water. 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 What is this channel about? Hi from San Antonio, Texas. I've actually been to San Antonio. It's very beautiful by the river there. I think there were a lot of restaurants over there. It was nice. So welcome to everybody. Welcome to Puma Fist, Sufyan, John. Puma Fist again. Groove Toot. That's right, I didn't read your username. Thank you, Groove Toot. So this channel is about the kitty cats who apparently they're fighting right now. I did not anticipate this drama to be happening in the hallway. There is some hallway drama, guys. Not sure what can be expected here. Usually they're very loving. Are you into transfinite arithmetic? I don't know what that is, Puma Fist. You should definitely tell us what that is, and I'll read that out to the people. So I'm always happy when people share some kind of facts in the chat, if they want to say something and share something that, you know, from their country, or there is somebody who... Suji Baji. Shona. Okay, I'm so sorry. This is not Baji. Suji. It's okay. It's okay. It's okay, Suji Baji. Sometimes if I soften my tone, they also soften their attitude. It's okay. It's okay. Karnashana. Cherdao. Cherdao, babu. Rag karna shona. Karna rag. Oh. Rag karna, babu. It's okay. Sorry, guys. There's a fight breaking out here. Thankfully, Suji's the one who is attacking Baji. If it was the other way around, I'd probably have to intervene more firmly, because he's much bigger than Suji. I have no idea what it is, but it makes me sound smart. I'm in physics. Are you... Ooh, Groove Toot! You're in physics, huh? Amazing. I'm in physics right now. Are you a teacher or what? Do you mean you talk about physics on these lives? Yes, exactly. So I talk about physics in these lives. We've been covering a lot of different topics. We actually covered modern physics in the sense of the 20th century physics. So pretty much the 1900s, early 1900s, 1910s, 1920s, 1930s, including relativity, general relativity, special relativity, developments in quantum mechanics. That's what we kind of shared. a lot on these lives, in the last several lives. And then I started to talk about dark matter more recently. And yesterday I covered dark matter candidates, actually, from this book right here. So because, so you could go back to the lives in the past and see that we covered this book called Einstein's Cosmos by Michio Kaku. That was one of the books that we referenced, especially because it's a very accessibly written book, which also covers a number of physics topics and also helped me to cover sort of the history of those times in the 1900s, leading up to World War II, especially, during which, of course, a lot of the physics developments were disrupted by a focus on the atomic bomb, things like that, things of that nature, largely the 20th century. And then we started to get towards the ramifications of all this work and how it transpired to the 21st century physics, where we are now, especially towards the end of the night, so like 1980s and 1990s, what those efforts looked like. We kind of got into that towards the end of that book. So then, now I'm sort of more in the current part of modern physics and talking about dark matter and things like that. So yeah, that's so cool. Awesome. Groovetooth says, that's so cool. Thank you. Groovetooth says, I toured a college and did an astrophysics class, and talking about black holes was one of the best classes I've ever been in. Yes. I actually helped to teach a black hole class myself. So what is dark matter? That's a great question. So basically, in our galaxy, they found that there is perhaps this extra matter that is towards the halo of the galaxy, and they could not account for it. It did not contribute to the luminosity in the galaxy, but it contributes to the mass. And basically, they were not expecting, first of all, this mass to be there, out there in those parts of the galaxy. And because it does not interact with light, it does not give us luminosity, which is basically primarily the way to find mass when it's ordinary mass. And so I'll show you the curve. There is a famous curve that is shown, especially as a proof of why they need dark matter, why they think that there is dark matter. Actually, I covered this yesterday's live, but because you ask, we will cover it again now. Dark matter is nonsense. Well, it depends what you define as nonsense. If you say that dark matter has not been found, as in the particle nature of dark matter is unknown, that would be correct. If you're saying that none of the dark matter candidates have been confirmed yet as a viable candidate, that would also be correct. I'm trying to find where, so I had it marked before because it was my last live. How is it studied if it's not on our planet? I don't want to interrupt you though. If we can't even fully explore our own oceans, how the heck do you think anyone knows anything about space? You could study astronomy to learn more about that. So here what I'm doing is going to page 442. See how this book is a textbook written by Barbara Ryden and Bradley M. Peterson. And this textbook is a staple textbook for a lot of astrophysics and astronomy majors. So because I also cover popular science books on the channel, I figured it's worthwhile to also reference actual textbooks sometimes so that you know that, well, this is how it's also taught in a university. So it's not like something, something that doesn't have, that's not backed up. You know what I mean? So basically, let me show you this curve. See this curve? So, I'm not an expert in oceans, and I'm sure there's much to learn about oceans, but you'd be surprised how much we both know and don't know about space. And I'm sure I'd be very surprised about how much we don't know about the oceans. Indeed, the oceans are, I'm sure, extremely difficult, very difficult environment. But just because we don't know everything about the ocean does not mean that we don't know something about space. We actually have been studying astronomy for hundreds of years. Back in the day, I'll give you a little spiel on astronomy for a second, because my background is both in physics and astrophysics. And I Oh, nice. Oh, thank you. And I actually was a teaching assistant for both physics and astronomy. So it's sort of my thing. GroupTude is saying this is probably the coolest live streams I've come across. You're so engaging. Thank you. My favorite book is The Demon Haunted World Science as a Candle in the Dark by Carl Sagan. Ooh, cool. So basically, let me just say this because it'll kind of lead us to some other topics as well. You know, for the longest time, we actually have been students of astronomy. We have looked up into the night sky. One of my favorite things is the night sky, full of stars. Actually, it turns out most of the things that you see in the night sky, those bright little things, most of them are actually galaxies, not stars, distant galaxies. And sometimes if you go to a really dark place, like I think the last time I saw the Milky Way galaxy, our own galaxy's disk, was when I went to a very dark place. I was by the ocean. Another one of my favorite things, the ocean, but I don't know much about the ocean at all. But if you're at a very dark beach, for example, and there's not a lot of light pollution and not a lot of what do you call? Not a full moon. As much as I love the moon, actually, it can be a source of light pollution for astronomers. So when astronomers are trying to observe something in the sky, they don't want they don't want the moon's interference. But for the longest time, hundreds of years, maybe thousands, we actually have looked up at the night sky. We've seen how things have changed, and we have done astronomy with visible light. So everything we see with the naked eye, of course, like we can see a cat right now, we can see my home. If we go outside, we will see a few stars. This is in Boston, though, so you can't see the full night sky full of stars. But if we go to a really dark place, we will see the night sky full of stars and some planets and some galaxies, lots of galaxies, actually, but we just call them stars as a layman's word. But these are what people used, just visible light or optical light to do astronomy. But we've come a very long way since then, because now we also do astronomy with X-rays, with radio telescopes, and guess what? With gamma rays, like we can even detect gamma rays from outer space. And so we're not just limited to the visible light. So astronomy has come a very, very long way in its observation capabilities. And we have basically all these different detectors, telescopes, things like that, to get light in its different forms, in different frequencies of light. Gamma ray, X-ray, these are all examples. Radio waves, these are all examples of light. So that's just light. But guess what? We even do astronomy now with particles. I worked on an experiment. How do you use X-rays in astronomy? Well, the Chandra Observatory is an X-ray observatory. So we can make our detector be able to detect X-rays, the X-ray frequency of light, and some very important observatories are actually picking up on X-rays. So being able to see X-ray is very important. If you just, us human beings mainly, obviously, we see visible light, but the universe has more than visible light. We just can't see. Like our eyes can't do X-rays, and our eyes cannot do radio waves, and our eyes cannot do gamma rays. Gamma rays are extremely small wavelength, and they're kind of dangerous, actually. So I'm kind of glad we can't do gamma rays. So if we had to pick up a gamma ray, basically, at that point, you're utilizing probably the particle nature of light. Gamma rays are very energetic because it's very high frequency type of light. So at that point, you're probably counting the number of photons that's hitting your detector, just as an example. So depending on which frequency of light you're trying to observe, it affects your type of detector. A gamma ray is going to be a very particle-y type of light. A radio telescope is going to be a very wavy type of light. So it's both of those are light. Radio wave is a type of light, and gamma ray is a type of light. But very different wavelengths or very different frequencies. So your type of detector or type of telescope will be different. The Chandra, Chandra, Chandra. Chandra is moon. It means moon in Sanskrit. But anyway, there is an observatory called Chandra, and it's an X-ray observatory mainly. So so basically, that's to say that astronomy is now done with more than just the visible light. It is done with all kinds of light. And not only that, it's even done with particles now. That's how far we've come in astronomy. So we actually have a lot of tools to study space by opening up new ways of detecting what's out there and new ways of designing detectors. We actually can study space and look very far indeed, depending on which detector you're talking about. So I actually said at one point, because we were covering so much of the 20th century physics, and we were seeing these astounding developments like special theory of relativity, which gave us like the relative nature of space-time and like mass energy equivalence, the E equals mc squared equation, which was eventually also leveraged in atomic bomb development. Obviously kind of sad, but all this mind-blowing stuff happened in the early 1900s, within 1920 basically. And then we also had developments in quantum mechanics. Like we understood that there's the atom and it has a nucleus even, and then the nucleus is, that's not it, we even have protons, and that's not it, we even have neutrons, subatomic particles. And the fact that there is a wave equation now for matter, Schrödinger wrote down the wave equation for matter, and then later on Max Born said that actually that is the wave equation giving us the probability of finding a particle, or the probability of finding, say, an electron within the hydrogen atom. So all of these things happened in the 20th century. What do we do now? What's the main thing that's happened in the 21st century that is sort of outstanding? And I would say the most outstanding thing is related to Puma's question here, which is how the heck do we do astronomy when we don't even know our oceans? Now, I'm sorry we don't know too much about our oceans, apparently. I certainly don't. But actually, this is it. Our technology in detectors, our ability to observe, measure, detect, has come just such a long way that we are actually able to study space much, much better than before. And we can pick up on all these different signals from what's out there. Our own galaxy, extragalactic, we can pick up on these signals with these different detectors. The way we experiment now, the way we measure now, the way we observe now has come such a long way. That would be the biggest progress that we've made in this century, in 21st century. Hi, Reese. All we know is what scientists say is out in space. What are your thoughts on human travel on Mars? The phases of the moon make no sense to me. Okay. How do you use X-rays in astronomy? We will definitely look at an example of how we use X-rays in astronomy. Even with telescopes, stars just look like blurry flickers. That's right, Puma. They're very far away. Actually, most of those are galaxies. And you're right. We are a little lonely on this planet in the sense that the things that we want to look at as astronomers are so very far away. So you're right. I mean, we have our friend the sun, and we have our friend the moon, and sometimes we see Jupiter, and sometimes we even see the moons of Jupiter. And, we have only one moon. So sad. I wish we had. And we have only one sun. So sad. Sometimes we see Mars, it's red and it does not flicker. Sometimes we see Venus, it also does not flicker, only because it's very close to us. It's actually very much like the Earth, except its atmosphere is poisonous. I wish Venus was the one that we were traveling to, because it would only take about a month or so instead of a year. It's much closer to us. It's much more like Earth in size. Only problem is we can't breathe. Venus. Oh, and it has an atmosphere. Thank you very much. Mars does not, as far as I know. It's closer to us and it's closer to the sun. Mars is very, very cold. I like it to be a little warmer. I wish. Oh, and let me talk a little bit about astrology. I'm a Libra, ruled by Venus. Not that I know a lot about astrology, but I know people like astrology more than astronomy, so I'll throw that out there. But anyway, I like Venus more than Mars. I wish we could breathe on Venus. Or that it wouldn't kill us. But yeah, that's my thought on Mars. Mars is okay. I guess there's iron on Mars, making it very red. All we know is what quote-unquote scientists say is out in space. Is that bad? You could be a scientist yourself, Puma, and solve this problem. Then you'll be one of us. Yay! Welcome! Join the club! Reese says, an upside-down smiley. Hello, Reese. How dare you miss our lives lately? Grave Toot, Puma, are you being serious or just being edgy? Puma says, I'm serious, Groove Tooth. That's okay, Puma, you're in the right live. We will work together. Don't you worry. It's a safe space for all the different varieties of minds and experiences. Because actually, I will say this, part of the problem is that scientists generally stay so busy with their science. We haven't, as a community, always communicated our results and our work to the general public in an accessible manner. Oftentimes, we publish in journals that cost money, that actually costs us money to write in or publish in with all our hard work, and then they don't even pay us. They actually then charge the normal people money to be able to read those articles. So I will say that the way academia has sometimes dished out its work is probably not the most accessible, and it leads to attitudes of, well, did we really do this or that, because we haven't really done as good of a job of communicating. And there are people who have done a lot of work, of course, to try to make science more popular, such as this book that we were referencing, Einstein's Cosmos by Michio Kaku. Michio Kaku has done a lot of work that even I don't understand, because a lot of this work is very complicated, very deep, very mathematical. You'd have to really immerse yourself in that field for years and years and years and years. I think part of the issue with physics too is it's a lifelong journey. It's not a fling. It's a lifelong love affair, not a short thing. Okay, so to get to the fun part of something like physics takes so many years of study that maybe people find it to be a little, not something they want to pursue. But if you don't pursue it, you're not going to be able to contribute either, or probably understand what's happening in the field. So I understand. Like, I took a lot of physics and I worked in that field, so I have this knowledge which I'm sharing with you today and on these lives, because I'm interested in communicating science. But I understand the sort of feeling of a little bit of mistrust or distrust in the field, because maybe we haven't, done it well. Scientists get paid through grants. They will say whatever they need to for a paycheck. What? That's crazy. Not you, Puma. What she said about the labs being posted. It's not science that people distrust. It's the money men. I agree with what you're saying to an extent, Puma. There is a lot of bad science, but science as a whole is based on reality, and rightly so. Yeah, I will say, so you're saying that the grants pay scientists, and so they publish, I will say this. If scientists, I would say, for the most part, scientists don't say things that they think are expected of them. That is actually kind of the point of being a scientist. If you wanted to just lie, there would be other professions that one could do and get paid a lot more money. So I'm not sure I would agree that most scientists lie. I would say that there are probably some notoriety involved in some some famous work or famous scientists may sometimes do shady things. It's not completely, that does happen. I'm not saying that I don't know any shady people in the field of science. But for the most part, for the large majority, like these professors and people who teach at colleges and universities and lecturers, me, I mean, I don't hold a formal position at this exact moment, but I have in the past. Like, we would make so much more money somewhere else. People don't really pick the academic or scholarly or research life to be rich, or to tell lies. Really, it's a labor of their passion, what they're interested in. And generally, it is to pursue the truth about something. You really want to understand something very deeply. Like, for example, to be a scientist, you probably have to have at least a PhD. I mean, a PhD is not a very fun experience if you're just trying to lie. I will say that. So, science is dictated by whoever is paying for it. Full stop. Okay, Puma. Clicker says, hi, he's so cute. Thank you. So, up to you to feel whatever you'd like to feel. But I just think that logically speaking, they would choose other professions if they had to lie. Anyway, you were asking about dark matter. So, here's a curve. This is orbital speed in kilometers per second versus distance from galactic center given in the units of parsecs. And you can see how this curve kind of becomes constant and even starts to increase. So now, without going into all of the details, because we went into the gory detail of this in the last night's live, what we actually showed was for our own galaxy. Ooh, let me also show you the picture of our own galaxy. This is an artist's impression, but we also, of course, have pictures of our own galaxy as well. But this is the artist's impression of the Milky Way. And you can see where the sun is here. Whoops. Where is it? Right there. See the sun right there? So we obviously go around the sun. I hope you believe that, Puma. So we do orbit the sun. And the sun orbits our galactic center, the galactic center of the Milky Way. So it's almost like the sun is going around our galactic center, and we actually know that it has gone around the galactic center only about 20 times. So in that way, the sun is actually only 20 years old. Little baby. Not that a 20-year-old is too young, but not too old either. The sun is a little baby, and the sun is around 8 kiloparsecs from the center of the galaxy, of our galaxy. So what they were hoping and expecting is that they did some math. So we went into this in gory detail yesterday, so I don't want to repeat the whole thing. But basically, they expected that most of the mass of the galaxy is going to be within that 8 kiloparsecs, where it's also shown to contribute to most of the luminosity. See, it says in this sentence right here, most of the galaxy's luminosity is provided by the disk, whose brightness falls off exponentially with a scale length of our scale around 3 kiloparsecs. Thus, most of the galaxy's luminosity lies inside the sun's orbit. Now, because they know that, they expected that, well, most of the mass should be within that orbit radius as well. But then they found this orbital speed with respect to galactic, or with respect to distance from galactic center. The orbital speed, so let me read this sentence. It will make it clear here. Most of the, I just read that. Observation of stars and gas clouds in our galaxy reveal. So they observed stars and gas clouds in our galaxy, which revealed that the orbital speed v in the disk does not fall off with distance from the center. Instead, all the way to the outer fringes of the disk, the orbital speed is constant or even slowly rising with radius. So just imagine they expected most of the mass of the galaxy to be within our same orbit distance. Some could be, a little bit closer to the galactic center. There's a lot of mass, we know. There's a supermassive black hole at the center of the galaxy. So we know there's a lot of mass right there. But then, all of the mass, including us, the solar system, lies within 8 kiloparsecs radius length from the galactic center. They thought all of the mass was right there. And based on that, they expect the orbital speeds of the things that are closer to the edge of the galaxy. So they were expecting that the orbital speeds there, sort of far away from the center, would be slowing down. But they saw that the speeds were remaining constant, if not slowly rising, which gave a whole new picture with this equation for the mass. And it turns out that there was all of this extra mass. And the leading explanation for that is called dark matter because it's dark. So let me read this. Dark matter might also be called invisible matter or maybe transparent matter, but dark matter is the name that has stuck. So we don't know what dark matter is, my friends. So we call it dark matter, as in we have candidates, we've proposed candidates for dark matter, but we do not know what it is because it's not been confirmed yet. The work is ongoing. So now we are in the current state of physics, and so far, we do not know what dark matter is. So if you ask me simply, the answer is we do not know, but we can discuss various candidates. Parsec is spelled Parsec. Black holes are theoretical. Gravity is still a theory? Oh, really? Gravity is still a theory? What's your theory? Do you think if I drop the pen, it'll drop? Oh, it did. Okay, so it does work. It's not just a theory. Let's see. Clicker says bye. Oh. If matter can never be created or destroyed, how does it have mass but not be seen? If matter can never be how does it have mass but cannot be seen? So the fact that it cannot be seen means that it does not interact with the electromagnetic force, or that it does not interact with light, with photons. It does interact with gravitation. So in theory, something could have a mass and not interact with the electromagnetic type of waves. And then, that's, it would, so maybe I should read about the dark matter candidates, and it would kind of help with this maybe. Reese said, what did you ask, Reese? Reese says, it's not science that people distrust, it's money. Rightly so. And COVID as a whole. COVID? You have to look at the motives, like if a certain study on, let's say, a certain drug is being funded by a big pharmaceutical company, that study may be screwed because they want certain results. Oh, I see. Pharmaceutical. Got it. But most scientists just are looking for the truth. Yes, that's a good point. I did not put it in the context of pharmaceutical. I know nothing about pharmaceuticals. What is a parsec? We will get to the definition. I'll show you the definition of that. It's a way in which astronomers basically quote distances. It's a unit of distance. Black holes are theoretical. Gravity is still a theory. That is not the case. Gravity is very much proven with experiment. Black holes are not theoretical. We have observed black holes. So out of dark matter, and dark energies, we actually, in the last century, we basically came up with the terms dark star, which is basically black hole. And they actually thought that these things were very bizarre and ridiculous and we would not find them, but we have found them. They're definitely very real and very much observed and not too big of a deal. Gravitation, we know, is definitely a thing. He or she is so cute. This is Baji, thank you. I see we still can't talk about it. Talk about what? If matter can never be created nor destroyed, how does it have mass but not be seen? I read that. So that's the challenge with dark matter. It does not interact with photons or light, but that does not mean that it cannot exist. We just don't know what it is exactly yet. There are things, though, that do not. So, for example, neutrinos do not interact with the electromagnetic force. Neutrinos do not have charge. They're a type of lepton and they interact through the weak force. So, neutrinos were a candidate for dark matter at one point. I think they're not really considered super viable anymore because neutrinos are too low mass. But not interacting with the electromagnetic field is not the only way to exist. For dark matter, I meant gravity is still seen as a theory by the scientific community, not my words. Oh, okay. Gravity is still seen as a theory by the scientific community, not my words. I wrote a whole other thing which was clearly censored by YouTube. Oh, but I didn't even see it. I'm sorry. Gravity is a scientific law, but not theory. I think, Puma, I think maybe I just don't understand. Maybe there's some semantics that we don't have, we're not on the same page. That's okay. Happy to have you here and still do the discussion. Science has replaced religion. Trust the science is the new trust God. I don't know about that. Anyways, think of education as sort of a tool. Once you're educated, you can decide what to do, But without the education, I think it's hard to say and hard to judge things. So, but education can be a good tool to then do with what you would like. You can contribute to the field or some other field, or bring your own opinions to the world. So anyway, let's actually real quick talk about the dark matter candidates, because I feel like we already kind of talked about it, and some of you were not here yesterday. So because we don't know what dark matter is, first of all, it's very perturbing. We know that we also don't know what dark energy is. So welcome to the 21st century. There's a lot that we don't know. Turns out that ordinary matter is a very small part of the universe, and most of it is dark energy followed by dark matter. And the problem is that we don't know what dark energy is and we don't know what dark matter is. Now, someone was saying that scientists lie a lot. If we had to lie, why would we say that we don't know what dark energy is and we don't know what dark matter is? That makes us look really bad. So, for example, dark energy is basically, being pursued as a field by cosmology. Everybody in cosmology wants to know what dark energy is. And the, results we get is the results we publish. Do certain shady things sometimes kind of happen in academia? Yes, absolutely. But largely, if the field is saying that we don't know what dark energy is, then that is the truth. And why would we say that? It makes us look like fools, that we don't understand that what most of this universe is. So dark energy is most of the universe. 73% of the universe is dark energy, and we don't know what it is. So we should work on it. We should contribute to it. You know what I mean? The next thing is dark matter. Turns out, with all this type of math and observations of orbital speeds, and we mentioned briefly yesterday about dwarf galaxies. So not only in our own galaxy, but dark matter can also exist in other galaxies. And we will delve deeper into that in the future here. But basically, in our nearby galaxies, a lot of which are dwarf galaxies too, they play a role. And with all these different observations and sort of these indirect evidences. Direct evidence would be to directly measure and identify what is the nature of dark matter. But all this other evidence that we're getting, including that curve I showed you of the orbital speed versus the distance from the galactic center, is actually an indirect evidence of something more, something that is there, but we can't see it and we don't know what it is. But it is there. And so basically, to say that we don't know what dark matter is also makes us look really bad, actually. It makes it like, what? And because it's basically, we can, dark matter, I was saying last night, is sort of a both a particle physics and an astronomy question, if you will. So if you go into those fields, you might end up studying and contributing to what dark matter is. For example, because, so what did I say? Astronomy and particle physics. Well, for one, if dark matter is a thing that, you know, we should be finding, and we have an entire family of particles in the particle physics world, or in the standard model, or beyond standard model, whatever, we would like to know from a particle physics point of view, what is the particle nature, for example, of dark matter. We know that, oh, thank you. I meant to send a, oh, thank you. You should set up your donations on your streams. I would, thank you. Well, there is a donation PayPal link in my bio. I don't have the YouTube super chat activated yet. Once I get to that point in YouTube, I think you'll be able to see it. But I do have a PayPal link in my bio. Thank you so much for considering it. And Puma said that I am talking about a divine energy. You know, dark energy, divine energy, after a point, I don't care really what people think. I'm just doing my thing here, man. I'm telling you that in physics, dark energy is unknown and dark matter is unknown, and we should be working on that because a lot of people are working on it, and I'm trying to communicate the science here so that hopefully the public understands what these topics are and they can decide for themselves if they want to work on it or not. So anyways, basically, dark energy. Say if you want to study dark energy, because it's an open question at this very time. Say if you want to study dark energy, the field to consider would be cosmology. Now, it's a subtopic or subfield of physics, but just to kind of orient you, once you get into, say, a PhD program, the type of group you'd want to join is cosmology. I did a year of that because I had a few rotations in my PhD. So I did a little bit of condensed matter physics, something I don't know very much about. I did cosmology and then ended up actually doing particle astrophysics as my thesis. So I kind of moved around a bit, and I also did research during my undergrad years. So I just wanted to mention that these different subfields will help you to do different types of things. Dark energy is a much bigger problem, quite literally, because most of the universe is dark energy, turns out, and we don't know what physically it is, which is a big problem. But because it's much more of a universe expansion type of thing, it's much more in the flavor of, oh my God, the universe is not only stable, it's expanding. It's not only expanding, its expansion is accelerating. So it kind of stems from the work of Einstein over 100 years ago when he did general theory of relativity and wrote down the equation for gravitation for the universe, and basically had to include something called the cosmological constant, something that we still talk about now, over 100 years later, in order to stabilize the universe against gravity. He realized that if the universe only had gravitation as this large-scale thing that affects, matter, then why doesn't the universe just collapse on itself? There has to be something that's sort of against gravity. And he wrote it down in his equation, called it the cosmological constant, as a constant placeholder term, because he was faced with that very difficult question that even Newton had faced a while ago. But then, actually, what he was doing, reluctantly albeit, is trying to stabilize the universe against gravity. Turns out, over 100 years later, that not only did we need this stabilizing constant, but also the universe is not just stable, it's expanding. It's very much going against gravity. It's expanding, and its expansion is actually accelerating. So it wasn't really until sort of the 1900s, later 1900s, like 1989 or so, that we actually realized that it's not only expanding, but it's acceleratingly expanding. So that is when we kind of lost our minds, and then when we did further calculations and observations, we realized, oh my God, there's something called dark energy, we already was kind of calling it that because again, it's not something that interacts with light, so we can't see it. But there's some energy, something going on with the expansion of the universe, which we don't really understand what the physical nature of that is. So pretty much for this type of thing, you'd have to study cosmology, much more like a universe thing, okay? The universes type of study, smooth universe. So we have a book here written by Scott Dodelson that we will reference in terms of dark energy discussions when we go into that further, okay? So don't worry, we will get into it. The next thing is if you wanted to study dark matter, which is very different from dark energy, but also a big question, the number 2 question of the universe right now is dark matter. What is it? Then it would be either tackled from an astronomy perspective, because we can make observations of our galaxy or other nearby galaxies and try to understand things from that. So that would be tackled under astronomy. Or we can try to understand it from a particle physics point of view and try to understand what is the particle nature of dark matter. And if there is sort of a particle-y dark matter candidate, we can try to either theorize about it or do an experiment to test for it in a collider or something like that. So that would be a more particle-y approach. So those subfields would be where you would go to study that and contribute to that, okay? So we will go back to the discussion of um well, I think there is a fundamental way in which science differs from religion. Science actually follows the scientific process. Like there's a hypothesis, you can test it out, you can experiment, you can collect data, you can analyze the data, then you have to publish the data. If it makes no sense, you have to say that it makes no sense or not publish it because, at that point you don't have a result. If you don't find the thing you were trying to find, you say you didn't find it and you constrain the theory that predicts it. If you do find the thing you were trying to say you found, then you have to publish it and say that you found it. You have to do the analysis and do it so carefully, and basically to say that you discovered something, you have to discover it to 5 sigma, some really big confidence level, and you have to do a bunch of statistics and math and all of that to say you found something. So when somebody says they found the Higgs boson in 2012, that was not a joke. It was very, very difficult work that people had to do to set up that experiment, to collect the data and then to analyze it and do all of the math and statistics to then report it to a certain level of confidence that they discovered it. So I would say calling science religion is 5 sigma, not 25 sigma. Calling science religion is kind of insulting in the sense of the work that goes into science. I would say that that is probably the most insulting thing I've heard on this channel, and I've heard a lot of insults. So anyway, first candidate for dark matter that they considered was neutrino. A neutrino can interact with other particles only via gravity or the weak nuclear force. So if you're not aware, a neutrino is a type of particle and that we have discovered. So if I'm saying it's a type of particle, it's because there's a lot of data saying that it is a type. Anyway, we've already discovered it. It's not a mystery. There's a lot of work that, has been done to know that this is a thing. If I say that we don't know what the thing is, it means that it has not been discovered and we don't know. And we may have hypothesized about it, but we did not confirm it, okay? So, and to confirm it would be a lot of work. I'd have to reference the actual experiment data, all of that, the paper, everything. Right? So if it's in a textbook and it says that we know it, that's because a lot of work has gone into knowing it. So you can trust it, or not, up to you. But this is from a textbook. So the first candidate, where do we find neutrinos naturally? Well, the sun makes The sun makes a lot of neutrinos. All nuclear reactions, most of them make a bunch of neutrinos. Let me read these comments. 5 sigma, not 25. Data is only published. Okay, whatever. Where do we find neutrinos? So, who is we? Well, we is we is the field of physics, physicists. There's people who work in labs, who put their heart and soul into science. Those are the we's. Lots of people. Have you ever been in a university, in a lab, in a scientific lab? There's such places where you can go work and be a part of the process if you'd like. So, who is we is that? Lots of students, grad students, undergraduate students, researchers, research staff scientists, technical scientists, technical staff, professors, assistant professors, lots of people across the world are the scientists who is the we. And generally there's a subfield, within the field of physics or science who will be doing the experiments that are to do with, for example, neutrino experiments. So, you were asking about neutrinos. So, okay, let me just say, broadly speaking, in particle physics, there are 3 types of particles, okay? These are leptons. Leptons, an example would be the electron. I'm sure you've heard of the electron. It is the particle that is involved in like every chemical reaction. All of chemistry is basically electrons moving around, right? So that's a type. I'm just giving an example of a lepton. Neutrino is also a lepton. It's in the lepton family. It's actually a cousin of the electron, much, much lighter cousin of the electron, and it has no charge. So it does not have charge. And if you read about it, you will see that it interacts through what is called the weak force. It's a different type of force than the electromagnetic force, okay? So again, particles are leptons, quarks, and bosons. So there are three types of particles, broadly speaking. Leptons, examples would be electrons and neutrinos. Quarks, examples would be the up quark, down quark. These make up the protons and neutrons. Sorry, sometimes I misspeak. It's neutron is what's in the nucleus, right? The neutron is not a fundamental particle. The proton inside the nucleus is not a fundamental particle. They're made of quarks. And so quark is a more fundamental particle and is made and is one of the type of particles. The last type of particle is bosons. Boson, an example of it would be photon, which is what light is. So those are the types of particles. If you study particle physics or get a quick overview of particle physics, you will see there are different families of particles. And so naturally, when we first understood that there is this dark matter, like there is this extra mass out there in our galaxy, outer regions, where we didn't think there was this mass. People were very, that was a very big deal. People were dumbstruck. They were like thunderstruck. This is like super unexpected. So they thought, oh my gosh, are these like neutrinos? Is there like a ton of neutrinos hanging out towards the outer parts of the galaxy or something? Because because neutrinos only interact with gravity, like they have a mass and they interact via the weak nuclear force. So they don't interact with most things. Like they don't interact electromagnetically. They don't have a charge. Like if you put out a magnetic field, it's not like you're going to affect a neutrino. Neutrino does not care about electric fields and magnetic fields. It's a very introverted particle. It's also the particle that I used in my own work. When I said I did particle astrophysics, and I was earlier saying that we now do astrophysics not just with the visible light, but we also do it with particles, I meant something like the neutrino, actually. We can do astronomy with particles like cosmic rays, which are just charged particles, and also particles like neutrinos, which are not charged, but they're a type of lepton, and they interact via the weak force. So just imagine sort of the course of events here. If you found that actually you did not know that there was a bunch of extra mass in the outer parts of the galaxy where you did not think there would be more mass, and you can't see it because it did not contribute to your luminosities, and astronomers just find this thing, what would you naturally think? And if you've just recently also discovered all these particles and particle physics is a thing now, and you've discovered the neutrino, what would you think? Oh my gosh, is there like a bunch of neutrinos hanging out there that we just didn't account for, and so we don't know? So that was actually a very naturally the type of candidate that they thought about. Can't blame you for the mistrust. Theologians get paid to research. Who is we? Okay. In Abrahamic religions, you also have the big three. What do you mean by fundamental particle? Like a neutron isn't fundamental. What's that mean? Happy Thanksgiving. Hi, Jason. Happy Thanksgiving. Happy Thanksgiving. So, a fundamental particle is basically something that does not break down into more fundamental particles. So, at first, we might have thought that an atom of a hydrogen atom, like a hydrogen atom, we could have thought that that's a fundamental particle, but it's made up of even more smaller particles. So, it's not a fundamental particle. Atom has a nucleus, it has an electron. The nucleus, we thought, oh, maybe the nucleus is a fundamental particle, but actually, no. The nucleus inside of it are protons and neutrons. In the case of the hydrogen, it's just got the proton. That's it. It's a very simple atom. But that's what I mean by fundamental particle. It's just whatever we pretty much, I mean, if you told me tomorrow that you have an experiment that shows that quarks can be broken down into something more, then I would have to correct myself and say, oh, actually, there's this other fun. But at this point, the fundamental particles that we know of are those three categories that I mentioned broadly. There could be something I'm missing, but basically, most of the stuff that we know, ordinary stuff, is those types of things: bosons, leptons, and quarks. Does that make sense? Prove a neutrino exists. You could go to the South Pole. There is an experiment there called Ice Cube. This is education. Education means that I'm giving you tools to verify this yourself. I don't really owe you anything. I don't have to prove anything to anybody on the street. But education is about learning and getting information that you can believe or not. But it's understanding something and getting the tools to then go do it yourself. We don't have to prove anything to anybody. It's up to you. You can discover the next particle for all I know. You could be a non-believer of particles today and discover a new one tomorrow. So anything can change. We believe in evolution. We believe in learning, studying, improving, contributing, and using information and education as a tool to then do something yourself. It's not like I'm trying to have a debate with you or argue with you. You know what I mean? Like, it's not really about that. There's no ego. It's just nature and trying to study it. So, okay. But if you want to go to the South Pole, there is an experiment there called Ice Cube. If you can't go to the South Pole right now, you could Google it and then learn a little bit more about it. And then, you'll have more information than you did before you did that. You know what I mean? It's more in that vein. But honestly, again, say you're like, oh, but no, I have to go to the South Pole. You could get a job at the South Pole. They really need people actually to work in Antarctica, especially during the winter. During the austral winter, you'd be surprised. They need people there, especially to work in power and the kitchens, and some of the best cooks in the world actually work in Antarctica. So you have the opportunity. Science is not just for the privileged, even though sometimes it happens to be that way. But if you wanted to do science, you can. You could actually work in Antarctica. I'm not kidding. And then you could learn more about this experiment. You could ask anybody, hey, how do I learn more about Ice Cube? And they'll probably take you on a plane. Actually, if you go from New Zealand, you'd first go to McMurdo Station, actually. It's closer to the coast. Then you would take another plane, and that would go to South Pole. So Well, Google is just one example. What I meant was you could do a literature search on Ice Cube. You could Yahoo it, whatever way you feel you could learn more about Ice Cube. They actually measure neutrinos from astrophysical sources. There are also other. Okay, you don't like Ice Cube. Fine, go to a different neutrino observatory. There could be you could find a more sort of low energy neutrino experiment that's catching solar neutrinos, maybe, if you don't like the astrophysical ones, because Ice Cube. So let me real quick mention this. The Puma is asking wonderful questions. It's leading to a lot of nice discussion. So basically, neutrinos, other people were asking about this too. Neutrinos are very tiny particles. We can't, we don't really feel them, but we're getting hit by many of them, especially from the sun. The sun makes a ton of neutrinos too, and those go right through us, lots of them. Because if it's a low energy neutrino, it can basically, because it's so small and it does not interact with other things too much, except through the weak force, like I was saying. So it actually can go through things really easily. Because just think about it. If you were somebody that interacted a lot with other people, then you'd it's almost like, say you're going through the earth and you don't interact with anything inside of the earth, then you kind of just go through it. It's like almost like the earth is kind of transparent to you. But if you were, say, like a proton and you are charged, you might stop and interact with something and make a, I don't know, different, you know what I mean? Like you would interact more. And so then you would be stopped. So that's one way of thinking about when you think about why do some particles just go through things and other particles don't? They get stopped. What does stopped mean? Stopped just means it interacted in some way and made something else, and so that's why. Anyway, but neutrinos are highly introverted, highly non-interactive kind of particles. And depending on their energy and depending on their source, you would actually set up different types of detectors. If you want to detect the ones from the sun, they're not very high energy. There are lots of different detectors for that. There's some in Japan. There's some in other parts of the world. There's also one a neutrino observatory in the Mediterranean Sea. If you don't like the southern hemisphere, which I think is the better hemisphere, because the northern hemisphere is too overrated. Too many people here. The southern hemisphere, of course, has Antarctica. Antarctica has a bunch of neutrino experiments. But say you're like, oh, that's too far. Well, in the Mediterranean Sea, there is a neutrino experiment. It's called Antares, Antares, Antares. So you could study up all of the different neutrino experiment examples, and they're done, pretty independently, all different groups of people. And are neutrinos carried by protons? How do they get from the sun to us on Earth? They're made in the sun when the sun is converting hydrogen to helium as sort of a side product, and they just come to us on their own. They don't need to be carried by the proton. They can be made from protons, like a proton. Depending on the reaction, depending on the nuclear reaction, a proton could make a neutrino upon interaction with something. But neutrinos are just like another particle. They can just come to us. They can just fly to us from the sun. Lots of them are constantly doing that. Solar neutrinos. So you can, in other words, there are people who study only solar neutrinos. So it's a whole thing. You could look up all these experiments that study solar neutrinos and do that yourself. So, yeah, they're not carried by protons, but they can be made from protons. Basically, if a proton interacts with a photon, you could get a neutrino as a side product. Basically, the way I like to give the analogy is that, you know how all chemical reactions, so this analogy is not perfect, so don't take it at total face value. I'm just trying to give an example, sort of an example. So you know how in chemical reactions, pretty much there's always an electron involved, like you get the electron as a side product. Basically, in nuclear reactions, neutrino is kind of like that. Like it's made along with other things, but it's like kind of involved. Like it's in there somewhere. At some point, you'll get a neutrino out of each of these like nuclear interactions, basically. So subatomic particles, when they interact and when they do things, they basically end up making a neutrino. And so yeah, cool beans. Oh, perfect. Thank you. So neutrinos are basically magic. Maybe. I mean, depends on your definition of magic. I really don't know what your definition of magic is. So could be. So basically, neutrinos are made in all kinds of nuclear reactions. So there's an abundance of neutrinos. So it wasn't too crazy actually when they found that there's this extra mass to think that it could be neutrinos, given that so many processes make neutrinos. It's not crazy actually to think. So let's read that particular paragraph to tell you what happened with that particular dark matter candidate. So the first candidate is the neutrino. A neutrino can interact with other particles only via gravity or the weak nuclear force. The weak nuclear force is weak indeed. The overwhelming majority of solar neutrinos, the ones I was just now mentioning, the overwhelming majority of solar neutrinos zip through the sun as if it weren't there. So yeah, the neutrinos will zip through dense, massive objects, or even whatever. Like it depends on the energy of the neutrino. I will say there's a caveat there. If it's a very energetic neutrino, other types of interactions can happen. But a lot of neutrinos that are lower energy, the ones from the sun, MEV type of energy neutrinos, will just zip through things. Since neutrinos snub photons just as they snub other particles, they are a possible candidate for the dark matter if they have enough mass. Recent experiments indicate that the three flavors of neutrino, electron, muon, and tau, have masses that differ from each other. So there's three flavors of neutrinos too that they found: electron neutrino, muon neutrino, and tau neutrino. Guess what? The three types of leptons are electrons, muons, and taus. Those are also leptons. One lepton that you're probably really familiar with is the electron, but there are other leptons as well. They're called muons and taus, other particles that we have also discovered. And associated cousins of them are the electron neutrino, the muon neutrino, and tau neutrino. So this is the lepton family right there, and all of which have been measured and discovered. And it wasn't easy though, because these are very low mass particles. So I remember even, during the last 10 or so years, getting the mass of each of these is not easy, okay? Although the exact mass of each flavor has not been determined, there are fairly strict upper limits on their mass from various experiments. So because these are very low mass things, there are strict upper limits. They might not know the exact mass, but they know the upper limit. You get what I mean? Like sometimes experiments, that's basically the result you get out of an experiment. Even though neutrinos are very common particles. So yeah, as I was saying, they're made very commonly in a lot of different nuclear interactions. Their low masses mean that they contribute at most a few % of the dark matter present in the universe. So basically, they considered neutrinos as a dark matter candidate. And it was not a crazy consideration, given that neutrinos also don't interact much other than with gravitation. Even then, they have low mass, and also they interact with the weak nuclear force, but they interact very weakly. Most things they don't interact with, so that would have explained why dark matter, we can't see it, it's invisible basically. But the problem is neutrinos are so low mass that with all the estimates and things, what they kind of expect how much of it to be there versus their mass, it just kind of doesn't add up to give us all that dark matter that we expect in the galaxy. So although not a crazy consideration or not a crazy first candidate to consider, it's not considered to be super viable as a lasting dark matter candidate. Let's say I want to do a project on particles and want to run an experiment on certain particles. Are there any that you can do at home? I think at home kind of experiments are probably more just chemistry experiments where the particle, you know what? I'm going to think about that. I'll think about if you can. That's actually a great suggestion. I wonder if there are toys that let you basically detect. Yeah, I don't know. I was thinking that at home type of experiments would probably be something to do with chemistry, you know? Like there's a lot of people who show at home chemistry experiments, and chemistry obviously has to do with particles at a more fundamental level, but at the chemical level people don't necessarily think about them as as the most fundamental particles other than for the electron. I'll think about it more, but that's a good suggestion. I wonder, you know what would be a great idea is if we could make like an at-home neutrino detector, like just to detect solar neutrinos. Oh my God, that would be cool. I just don't know. Yeah. They need, I mean, the problem, you know what the problem is? Basically, you know what they do is basically for something like the neutrino, it doesn't it doesn't interact much, right? So basically, you have to set up a very large body of detection medium to eventually catch a neutrino. Basically, you have to increase the chance of some interaction happening, even if it's sort of a indirect kind of interaction, and then you figure out a way to get the signal out of that. So it's more often than not, a neutrino detector experiment is basically going to end up needing like a big mass of something, some dielectric, it could be water, ice, salt. So it ends up being something like that. So I'm trying to think if that could be done in sort of a smaller scale. But yeah, I don't know. The problem is that chemistry is not theoretical particle physics. Oh my gosh. We finally agree. Chemistry is not theoretical particle physics. You're right. Agreed. Because chemistry is basically applied physics, I mentioned that. But you're absolutely right. It's not theoretical particle physics. So you do believe in science, Puma. You've given yourself away. So, okay. The second candidate for the dark matter, going back to dark matter, is the WIMP. The term WIMP is an acronym for weakly interacting massive particle. Supersymmetric extensions to the standard model of particle physics predict massive particles that interact only through the weak nuclear force and through gravity, of course. Think of them as these obese cousins of neutrinos. Particle physicists give them hypothetical particle names like photinos, gravitinos, axinos, neutrinos, and gluinos. However, since they are massive and weakly interacting, astronomers lump them all together under the generic label of weakly interacting massive particles. So basically, because the neutrino candidate fell kind of short to be a dark matter candidate, oh my gosh, look at Baji. He came running with his little toy. Baji. Look at Suji Baji, they're playing. Baji came running with his dog toy. Aww, hi babies. Baji came running. Aww. So basically, the WIMP came about because they were like, well, we considered neutrinos to be as a candidate. Oh my God, Baji is playing. Baji! Baji! Aww. Oh, my babies. Thank you, God. So, they basically considered neutrinos, right? And they saw that, well, we fell short. Neutrinos were too low mass. So then they basically imagined particles this is an imagination, okay? This has not been confirmed, so I'm going to just tell you now that this is a hypothesis. WIMPs, when they're discovered, if they're discovered, they will be confirmed. We are still carrying out experiments and work to see if we can measure WIMPs. So they're just a hypothesis at the moment. So we call it a candidate, dark matter candidate, meaning still a hypothesis. We have not seen them yet. But basically, it's very much like a neutrino, but giving it more mass. It's kind of like a dream. Like we dreamt it up as, okay, neutrinos didn't work. They were weakly interacting. That was really good, but they were too low mass. So there could be maybe something that's, like a fatter cousin or something, an obese cousin of the neutrinos, which could maybe work. And because particle physics has something called supersymmetry, which allows sort of other states of particles to be a thing, of course, to say that it's a thing, we'd have to measure it. And we'd have to give you the analysis and the data and the result after a lot of data being collected and analyzed and things like that. So it would not be, when it's theorized, we call it a theorized particle. When it's actually discovered, we'd have to do a lot of work and experimentally prove that it exists. So they haven't found it yet. Thank you. Good night. Thank you, GrooveTude. Good night. Thank you. So they haven't found it, but it is a dark matter candidate. It's almost like we're trying really hard to please find a dark matter candidate, and it's almost like we have part of the picture. We know it has to have mass, it can't be interacting a lot. Well, neutrinos are too light. Well, is it a WIMP? Is it something like a weakly interacting but more massive particle? So that's where the WIMP comes from. So that's a candidate. The next thing is the third candidate, okay? Although WIMPs have been searched for in particle accelerator experiments, they have not yet been found. So as I was saying, to say that something's been found, to say that something's been discovered is a lot of work. You have to get the data, you have to analyze, and you have to show with a lot of confidence statistically that you actually made a discovery. It's not an easy thing to do at all. There are some ongoing experiments and work in this direction, but we have not yet discovered in experiment a WIMP. So it is still just a candidate for dark matter, not known yet. And that's why we say we do not know what dark matter is, because none of the candidates have been confirmed, okay? So I must get some sleep also. Nice to catch your stream. Thank you. You can always catch the rest of it later on. You can come back and find the live video that after it gets uploaded. Thank you for joining. Thank you for being here. I honestly want to keep learning, but I need to go to bed. I subscribed. Thank you. Such a great teacher. Thank you. Divine energy. Perfect. I must get some sleep. Good night. How do neutrinos impact our day-to-day lives? I don't know that they do. Not everything is about human beings, Yeah. Pure science is not an applied science. We know that. We know that pure science is not always applied in day-to-day life. Yeah. Thank you so much. Although WIMPs have been searched for in particle accelerator experiments, they have not yet been found. Of course, since their predicted rest mass is quite large, again, hypothesized, right? WIMP is a hypothetical particle. So what we hypothesize for a WIMP is that it is very massive, compared to, say, a neutrino. Typically, numbers are 100 times the mass of the proton. You would not expect to produce them in the current generation of accelerators. So basically, this is saying that we tried to look for WIMPs, but we did not find them yet. And maybe the current generation of accelerators. The state of the experiments at this time is not expected to be able to yield these. However, the Large Hadron Collider at CERN is expected to search for supersymmetric particles with thousands of times the mass of the proton. Other experiments are searching for WIMPs in the same way you detect neutrinos. See, I told you that a lot of the dark matter experiments are kind of similar to neutrino experiments, potentially, depending on which one. So this is why I was saying that the dark matter is more of an astronomy and astrophysics and particle physics-y type of question, or the way that we're approaching so far is sort of that. I mean, if you find a different way to approach it, that would be fine too, but that's sort of the field you'd be in if you wanted to study dark matter. But basically, I was mentioning how there are neutrino experiments in Antarctica. Same way, there's actually at least one dark matter experiment that I know of that they're also setting up and trying to do in Antarctica. So basically, the motivation is, well, just like the neutrino is weakly interacting, and we kind of need certain special methods to find them and discover, measure them, discover them, whatever. Sort of the similar idea is true for dark matter if your hypothesis is something like a WIMP, right? So other experiments are searching for WIMPs in the same way you detect neutrinos, by building a really big detector and waiting for those very rare interactions mediated by the weak nuclear force. So far, there exist only upper limits on the WIMP interaction rate, but the search goes on, ... So basically, if you set up an experiment and you don't find a WIMP, then you actually get to set a limit on WIMPs. WIMPs can be hypothetical, but if you set up an experiment and you expect a certain measurement to give you a WIMP, and you have noise, you have other things also giving you signals, and even if a WIMP is just hypothesized, you still expect a certain kind of signal, probably, if you were to see it in your experiment. So when you don't see it, and by don't see it I mean you analyze the data, and to a high confidence, you're not able to really say that you got the signal from a WIMP, well, then you can still actually place a limit on WIMPs and say, well, either WIMP is not a thing, or WIMP is more rare than we thought. You know what I mean? Like something like that. So not discovering something is also a result. Actually, in particle physics, it's a very important result, and often a result that you have to make yourself content with, because so many particle physics... Hello, Suji. Hi. So many particle physics experiments actually end up maybe not discovering what they hoped to. So that's also part of life, and part of particle physics is that if you want to discover something, doesn't mean you'll actually discover it. But saying that you did not discover it also is useful result that you have to publish, and it puts constraints on certain theories that might have predicted the thing that you're hoping to discover. So there you go. So they probably have some limits. There's probably still some paper that would come out of the experiment and give you some limit on the WIMP, okay? So that's the second candidate that we just talked about. Now, this textbook gives us the third candidate for dark matter that we also considered. The third candidate is something completely different, the MACHO. The term MACHO is a slightly strained acronym for Massive Compact Halo Object. MACHOs are dim, dense objects with masses comparable to or somewhat less than the mass of the sun. So our sun, brown dwarfs, old cold white dwarfs, neutron stars, and black holes can all be MACHOs if they are located in the halo of our galaxy. So basically, they called one of the candidates WIMP, right? So there's probably like another camp of physicists who are like, we'll call our candidate MACHO. And it's going to stand for Massive Compact Halo Object. So they found a way to cleverly make that kind of work out. MACHOs, like any massive compact object, can act as gravitational lenses. One of the predictions of the theory of general relativity is that massive objects can bend the path of light. And early experimental support for general relativity came in the year 1919. Wow, over 100 years ago. Remember, Einstein had given us one of this particular prediction of general relativity, telling us basically that it can give us gravitational lenses. And in fact, that became sort of an important tool for astronomy. Go easy on her. Okay. So basically, they figured if these, if dark matter, which is in the halo of our galaxy, is maybe something that, we just maybe just don't see. Maybe we just like don't know that it is there. Maybe there's a bunch of compact, massive objects there that somehow we can't see. We're not very, good at seeing it. Brown dwarfs, things that did not cause much luminosity, maybe really old, cold white dwarfs. Old, cold because if it wasn't so old and cold, we would have seen it. It would have had more luminosity. Or maybe there's a black hole that we really can't see, although there's other ways of seeing a black hole by noticing, the behaviors of things nearby. So people are thinking, well, maybe are we stupid? Are there like things in the halo of our galaxy that we just can't see very well because, it's just not very visible, maybe really dark, maybe doesn't produce a lot of luminosity, but we're just silly, we can't see it, but it's there. So now they're thinking old, cold white dwarfs and brown dwarfs, things like that, and neutron stars and black holes. Like these are all things that we can technically observe, we have, but maybe there's some weird ones out there. Well, the thing is, Einstein helps us out with this because even if it's old cold and you can't see it very well because its luminosity is really low or something, well, a massive object, a massive compact object, as in there's a ton of mass in a compact object, like the mass of the sun, but within like a 10-kilometer radius of an object, well, it would still do gravitational lensing. It would still act as a gravitational lens, as predicted by Einstein's general theory of relativity. Hi, Yash. How are you? So machos, like any massive, but you see the sort of thinking here, right? Like they're really exasperated. If we can't see it, and it's still something obvious, like something massive, some object that we just can't see because we're not good or something at seeing, which we're much better now at seeing than before, then they want to rule that out, right? So how to rule machos out? Well, they would act as gravitational lenses. One of the predictions of the theory of general relativity is that massive objects can bend the path of light. And an early experimental support for general relativity. Remember that solar eclipse experiment that they did after Einstein's theory came out? Basically, they revealed that the sun had bent the path of some starlight by an angle consistent with the predictions of Einstein. So that was basically a confirmation of gravitational lensing all the way back in the last century. But something like that could be happening, with these massive compact objects if they are there. So because massive compact objects bend light, they can act as lenses, making distant stars appear higher in flux than they ordinarily would. So they're thinking, if these things are there and we just can't see them, well, they would still do something to other starlight. Suppose that a compact object, the lens, moves directly between us and a distant star, the source of the light. As shown in this figure right here, as the lens moves towards the source, as seen from our viewpoint, the flux of light we receive from the source grows larger. As the lens moves away again, the flux decreases to its original value. Thus, the light curve of the source was shown, as shown in this figure, will have a characteristic rise and fall. If the lens is a stellar mass macho, so now we have math that we can now do with this hypothetical macho, right? We can see the stars rise and fall. If the lens is a stellar mass macho and the source is a star in the Magellanic Clouds, for example, then the rise and fall typically occur over the course of a few weeks. Research groups have carefully monitored the brightness of the stars in the Magellanic Clouds, hoping to catch machos in the act of lensing. Although lensing events have been seen, there turn out to be fewer machos than are needed to contribute all the dark matter. Only around 20% of the dark matter in the halo can consist of machos. There's still plenty of room for WIMPs in the galaxy. Or something else. The author is being a little bit cheeky here. She's saying, or he's saying, they're both saying that if machos was all there is to dark matter, then we would have seen a lot more of this effect. Basically, the way we see it, even if machos were a thing, even if there are machos, as in there are compact objects out there in the halo that we can't see very well, but they're there, they're hanging out, they would give us much more of this gravitational lensing effect than what we observe at the moment. They would maybe account for 20% of dark matter, not all of it. And so what is the all of it? You know, what is the majority of this dark matter that we seem to have but don't seem to see, don't seem to be able to confirm yet? So those are the three candidates. Hopefully that helped. I'm good. What about you? And where are the kitty cats? They're having zoomies. So they're kind of like all over. But yeah, that was the dark matter candidates that I covered last night, actually. And covered it again today because some people were asking about dark matter. So again, there is a lot of research going on with dark matter. So what I say in one live is really not enough to cover the whole topic. But I wanted to give you at least what candidates we have considered seriously already and what sort of ended up in the textbook. Because if it was a serious consideration, and they've thought about it and they've put it together, then it would appear in the textbook. They don't just put things in the textbook that are like nonsense, right? So basically the most serious candidates for dark matter that people thought about so far are the neutrino, number 1, number 2 WIMPs, and number 3 machos, and that's in this textbook. And there's other candidates too that we can talk about in more detail, that's sort of in the more of the research realm at this time, and papers are still coming out and things like that. But this was to give you a flavor of a very big open question in astronomy, particle physics, whatever you want to say, in the universe really, which is what is the particle nature, or what is the nature of dark matter? What is it? What makes up dark matter? And we discussed 3 of the compelling candidates here today. And we also discussed it in more detail yesterday in our live yesterday. So today, I also wanted to cover somebody called Madame Curie. So basically on these lives, I've been covering a lot of different physics topics, a lot of different interesting topics like this. And we're going to do a healthy mix of both sort of science communicated in a popular way versus science from like textbooks and actual real, good information, good references. The popular books are also real books, but I think it's good to have a good mix of the two. It can be both educational and fun. So I actually have another book. It's on Madame Curie, Mary Curie, and I thought that I will get into it a little bit today as well. I actually named this live Madame Curie because I thought that that's what we'll mainly discuss. But there were a lot of good questions that were more astronomy related and dark matter related, because I mentioned that, because that's what we're mainly covering these days. But I think I'm going to mix it up with some more popular science as well. So yeah, this channel will cover both sort of popular science, as in science as communicated to the populace in the form of sort of more popular books, as well as science textbooks. So this book that we've been reading from, I'll just show real quick once again, is a very prominent textbook in astrophysics. It's called Foundations of Astrophysics by Barbara Ryden and Bradley Peterson. So just know that the information I will always mention exactly what is coming from where. And if something is coming from my own background, then I'll probably mention that. So that's what you're consuming here. I will take a quick break to find my other book. And actually, I need to get some water and things like that. So hang tight and we will keep going. Okay, we will actually put the phone here and I will show you sometimes I do this where I put the phone and I also put the book right there so you see where it's coming from. So we just covered this. Whoops, sorry. We just covered this book because as I boil my water, I want to put the phone somewhere. You know what it is? You know what it is? Yash, are you still around? How are you? There, you can look at that. And if you need this textbook, not that you have to buy it, we're going to be covering this book here on the channel. So, you know, I'm just letting you know the reference. I'm not saying you have to buy the book. And the other book that we will also get into is this one. Whoops, sorry. Here's one book that we just referenced, Foundations of Astrophysics. We just covered dark matter candidates from this, just so you know, okay? And then we will also get into this book, just because it's cool. This is a really cool book. We will also talk about this. Okay, that's what I named our live. Like I said, Madame Curie will be the live today, but we haven't started it yet. So this is next. We will talk about this in just a bit. I'm going to take a little break to make some tea. Get settled, get yourself a tea or snack or something and hang out. And if you're watching this as a video upload later on, thank you so much for joining. Thank you for being here. Please give us some comments and feedback on what do you think of the content and any questions you have, and I'll still address it at some point later on if I see it later. Okay? Thank you so much. We'll still be here. I never shared the live. So I'm telling people we just finished today's dark matter discussion. Going to cover Madame Curie next post. All right. I was so pissed earlier. I was like, this is the most insulting thing I've ever heard. I think I do probably come off like really sheltered when I say that, but it's true. This person was like, science is not real, scientists are all liars. I mean, how insulting. How very insulting. But now that I think about what I said, I was like, oh my God, science is all lies. And I'm like, that is the most insulting thing I've ever heard. I mean, I think it is a privilege to be a scientist. So yeah, maybe I'm a little sheltered and privileged, you know? Thank you, God. Thank you, universe. I'm like, I don't know what to say. Enjoy. Oh, God. I will get better at handling the comments. But I just couldn't help myself. I was like, this is the most insulting thing I've ever heard. Which people can be pretty weird. People have said all kinds of things, but I chose to be the most insulted by that, which is that science is not real. There has been some drama here. Alright, we just finished up dark matter candidates. We'll go to Madame Curie next. Give me just one more second, okay? Need to recover from this nonsense and make some tea, please. Thank you. Let me see what this guy said. I'm waiting for your live. Okay, send me the link. Oh my god. Oh, my best friend has a presentation today. I'm doing my YouTube live now at this hour. It's what I do at late nights these days. I'm telling my best friend. Jesus. Jesus. We will be back with Madame Curie. Stay tuned. Be right back. We will be back with Madame Curie soon here. Stay tuned, be right back. Thank you guys for your patience. I just need a second. I'm still laughing. I seem like a derp. I'm like a naive little scientist girl. So offended by weirdos saying that science is not real. Oh God. Such a much offended. Such drama. But yeah, no. I thank the universe for giving me the privilege of studying science and getting an education. Alright. Okay, where's my tea? Holy crap. It sounded like it helped somebody. So, this will be interesting because we'll talk about Madame Curie, but also we'll talk about women scientist role models, which can be sort of an interesting topic here. So, that's what we'll talk about here. Oh my gosh. It's I'm sorry. I'm still laughing. Oh. Fuji Baji. Hopefully I got everybody's comments. Look, Suji's also interested in the Madame Curie complex. So this is about how women scientists may suffer from a complex called the Madame Curie complex, and how women scientist role models may or may not affect us women in the scientific fields. Oh, I didn't see this comment earlier. Gravesuit was asking, are there good stars where you live, or is there too much light pollution? There is a lot of light pollution in Boston, but sometimes I can see more stars than I would have that I would have expected to. So, yeah. Ah! I'm from San Antonio, Texas. I'm going back and reading the initial comments that I may have missed. Okay, alright, so we will continue in just a second. Sorry guys, give me one more second. Had to boil the water. So, fair warning, I myself haven't read this book in a while, so I will be discovering along with you sort of the topics in this book. I vaguely remember that the author writes very interestingly about this complex, sort of, like a inferiority complex or a God complex or a superiority complex. Well, apparently there is something called the Madame Curie complex, and we will see what that is about. Okay, where's the teapot? Oh, I'm crazy. It's right there in the sink. Okay. let me start to give you some ideas. So this is the Madame Curie complex. It is written, of course, by Julie Desjardins, I think, Desjardins, I don't know, Juliedesjardins, The Hidden History of Women in Science. So, along with our dark matter topic, we will also cover this, okay? So, here's the introduction through the lives of women scientists. That's what we'll cover just now. Some fathers tell their kids about mythical home run hitters who won the World Series, or of courageous expeditions to Antarctica or the moon. Hi, Suji. My father's story to me was about Enrico Fermi and the scientists who created a nuclear chain reaction beneath the stands of the football stadium at the University of Chicago during World War II. Yay! Manhattan Project, so that's what we'll talk about next. As soon as I finish this. So it talks about having role models in science. And we will get a feel for the life of certain scientists as well, including, of course, Mary Curie. Look at this. Very blue. The tea is getting made. Here's Suji. Here's Baji. Here's Fuji. Hi, Fuji. Hi, Baji. Baji. Little Baj is over here. So we'll cover this book for a bit. So the author's father liked to talk about Fermi and the nuclear bomb. As a lifelong Chicagoan, Dad preferred this story to those about heroic men at Los Alamos. Yeah, I mean, Fermi Lab is outside of Chicago. It was at this moment under Stagfield, he believed, that brilliant men had convened for some greater scientific purpose. The only story as awe-inspiring was the one he told of the Founding Fathers who converged on Philadelphia in 1776 to establish, as Dad put it, the most enlightened democracy in the world. Both stories were so often told in our house that I could even remember the pauses built into their telling for dramatic effect. Whether he knew it or not, the message Dad conveyed was not only that science, like statescraft, bred greatness, but also that those talented enough to change the course of history were inevitably male. My father was in awe of the great men of politics and science, and I wanted to awe my father. I never aspired to run for office, but I did have fleeting thoughts about becoming a scientist. I started out on the right path, and early on I proved to be a whiz at math. In elementary school, I performed arithmetic leaps and bounds better than my peers. I remember my 4th grade teacher walking me over to the accelerated 5th grade class, while the other kids grappled with concepts I had already mastered. Fuji! They need a snack. 1 second. One second. No, baby. You timed me out for questioning things. No, I just wanted to stay focused on my thing that I was trying to finish. But you can be here. Focus on finishing my part that I was on. But you can be here. Welcome to the live. Science is all about questioning things. I thought you didn't believe in science. Now I don't know what to say. But thank you. Thank you. Keep on sending your questions. Wow, you're not nice. Okay. I don't know what not nice thing I did now, but okay. Bye. Good night. All right, we will get started with Madame Curie's complex. In fact, we have started to read the first page. Let's see. Okay, up and vertical and off, off and off. Just have to make sure everything is off. That one is off, plugged, unplugged. It's all off, off and off, off and off. Okay, so I have a warm Horlicks in a cup, drinking it. Oh dear God. Okay, so this author wanted to make her father proud by becoming a scientist. But she found that the scientific field did not have a lot of female role models. This was a bit of an issue. So she talks about that. So basically, my father was in awe of the great men of politics and science, and I wanted to awe my father. I never aspired to run for office, but I did have fleeting thoughts about being a scientist. I started out on the right path, and early on I proved to be a whiz at math. In elementary school, I performed arithmetic leaps and bounds better than my peers. I remember my 4th grade teacher walking me over to the accelerated 5th grade class while the other kids grappled with concepts I had already mastered. My excellence in math was short-lived, however. Hi, La Casa de Bombrel. How are you? How are you, my friend? In 6th grade, I was ahead by 2 grade levels, and by 7th and 8th grade, ahead by only 1. In high school, I hit my wall, turning in a mediocre performance in advanced algebra, and then doing miserably in trigonometry. Good morning. Hi. Invariably, boys were involved, for the ones on which I had designs didn't turn up in my history classes. But in math classes, where I deferred to their seeming expertise. What? In my senior year, I opted out of calculus altogether. Oh my gosh. Oh, that's a horrible idea. It infuriates me that I had succumbed to math anxiety at precisely the predictable moment for adolescent girls. Oh yeah, that's true. I have a friend who was really good at math when we were young, but then she did not continue when we were in high school. A lot of girls actually kind of stop going towards the more mathy side of things in the later years. Oh my gosh, that's right. Then, although I performed brilliantly in advanced biology, I had so little confidence in math that I avoided other science classes. In the one chemistry course I was forced to take, the teacher seemed openly hostile to girls, so I didn't approach him for help. Yeah, that can happen. Although I could have pursued biology in college, I decided that I didn't have a mind capable of serious science. My dad once confided to me that he thought things would have been different had I been a boy. He sensed that I had fallen prey to the prevailing tides. In his honor, here are the stories of scientists, ones that I hope will also inspire awe. Of course, they're necessarily different from his, since I'm asking new questions about heroism. I'm asking about the girls who did what I didn't, who felt social pressures not to pursue science but did anyway. I'm asking about the lives they led once they became women and certifiable scientists, and I'm asking about how it was that many of the best female scientific minds were ignored largely because they never were certified as scientists. These stories describe scientists my father never heard of, though some of them might have been under Stagfield had the culture of science been different. This book is not overly laudatory of female accomplishment in science, but it isn't a victimology either. To pity women of the sexist past or to celebrate women's progress in the enlightened present is to write without context. To find compelling stories in the 20th century, I had to leave Stagfield and sometimes professional labs and institutional science altogether. I had to write outside the narrative conventions of great history too, for when you boil them down, they're masculine to the hilt and perpetuate the invisibility of women. I aim to remedy. Women can never be the true heroines of great science, just wannabes and imposters, since the cast of such science is male by default. 20th century science has been buoyed by myths that create prestige in masculine terms, and thus it is not enough to provide a laundry list of the women who nevertheless managed to earn entrance and accolades into its elite circles. Such stories could never be anything more than fragmentary and compensatory history, filling yet another volume of exceptional women who performed outside their skins. I have had to question the concept of scientific heroism and define it by other means. Hi, La Casa de Brombril. What country is that flag from? Sorry, I have to ask. The drama of women's stories lies less often in extraordinary discovery than in overlooked details. Details that pertain to women's scientific work, but also to their private lives. Since both are inextricably linked, feminists have long insisted that the personal is political, and I extend that truism to assert that the personal and professional, private and scientific, are intertwined in these pages. To tell a connected story of women in science, my historian's lens pans out to reveal the contours of women's science careers generally, but it zooms in to look at representative figures up close, some iconic and others not successful in the traditional sense. Mary Curie, Jane Goodall, Rosalind Franklin, Evelyn Fox Keller, Lillian Gilbreth, Cecilia Payne Gaposchkin, Diane Fossey, Annie Jump Cannon, Beirut Galdikas, various Nobel laureates and women of the Manhattan Project appear separately and as a part of a whole to shed light on the ways American science has been experienced and imagined over the past century. Here it is. Suji head and Baji head. Interesting, right? While it might sound strange to bring together scientists from the lab and the field and the Nobel podium and the backroom, the physical and life sciences, academic and popular venues from the turn of the century and today, I tell their individual and collective stories to show how cultural ideas of gender have shaped the methods, structure, and meaning of science itself. Some may wonder how intrusive gender ideology has been of late, for sheer numbers seem to indicate that women have made progress in scientific institutions over the past century and that the trend continues. As I scan the admissions website of the Massachusetts Institute of Technology, I see that it currently boasts an undergraduate population that is nearly half female, and even a female president. When seen in the light, the president of MIT, not the president of the country. But that's another story. When seen in the light of the ratios of women to men in the U.S. Naval Academy's class of 2009, 19 to 81%, it seems that the culture of MIT and science generally has already changed in ways that the American military, yet another historically male bastion of prestige, has not. And yet, I couldn't help but also notice the data that was conspicuously missing on the MIT website. I wonder about the fields in which female students succeed most and what their outcomes are in graduate school or the job market after college. The website boasts of 197 female faculty members but fails to inform us how this compares with numbers of men or at which levels of promotion women congregate, although it pays homage to MIT's first female doctorate holder. In chemistry, the site fails to convey that she never achieved the pay or promotion of her male peers, and to mention that she was relegated to the women's work of domestic science. More important, it indicates nothing about the types of scientific questions pursued at MIT. How have women, whatever their numbers, actually changed the culture of the institution and the social ramifications of the work done there? I'm guessing that the data on female bodies walking the grounds at MIT looks better to prospective applicants than some of the data I want to know, but history tells me that deeper meaning lurks in these and other cultural silences beyond scientific institutions. In recent decades, we've applauded the heightened female presence in American politics, for instance, and yet anti-feminist legislation gets passed under women's watch all the time. So we're reading this book right here, the Madame Curie complex. We will learn a lot about Madame Curie here. Okay, where was I? So this is going to be an extremely important, interesting, view from the author. The 2008 vice presidential run of Sarah Palin underscores the point that peopling institutions with women will be no hard and fast way to change the sexist culture that pervades them. And thus, while no one disputes that more women occupy institutional science than ever before, I think that we need to pay more attention to the gendering of scientific culture in the end. Luckily for us, the personal and professional lives of women provide a lens for seeing this process over time. The stories in this book will enlighten, and at the same time, they may also inspire. I've written these stories as the problem of women in science continues to rear its head in 21st century popular discourse. Naively, I had at first assumed that the problem was no longer a problem at all and that a general consensus had been reached, that women are adept at science and that they simply need the opportunity to prove it. I've since learned, however, that present attitudes are more complex. So we're going to get into this complexity that drives some of the attitudes. I think we'll talk quite a lot about imposter syndrome actually in the book, so hang around, we'll get there. Most people I know think that women can be good scientists, but they also believe, consciously or not, that what makes women good scientists is the extent to which they deny their true selves to think like men. Knowing this, I'm afraid the women in science problem is far from licked. In January 2005, Larry Summers, then the president of Harvard University, managed to stir the pot when he remarked to an audience, including scientists, that women's relatively poor showing in science could be linked to innate biological difference. When I heard the early media reports, I was outraged. But transcripts reveal more ambiguity in Summers' statements than what the media first claimed. He attributed women's lower numbers in science to any number of factors, discrimination included. The essence of what he said is probably less relevant than the charged reaction that ensued, since it tells us so much more. Women's position in science will never be resolved so long as gender itself remains a hotly contested social problem. It seems that everyone has opinions on whether or not women have scientific ability, and some opinions are more informed than others. My intention is simply to bring the past to bear on them. Few of the women scientists who feature in this book entered these debates directly, but their work speaks for itself, dispelling claims that men are inherently better than women at science with their limited access to the professional training, resources, mentoring, and social networks of men. Women have occasionally asked different questions, used different methods, and come up with different explanations for phenomena in the natural world. For many, their marginal status in institutional sciences afforded their altogether different relationship to the nature they observed, as some became stewards and advocates for women, animals, and the environment. They expanded definitions of appropriate scientific work in the 21st century. Of course, the title of this book begs the question of Mary Curie's effect on these stories about American women and science. She wasn't American yet. The sheer number of American books and films written about her suggests that she is a presence we cannot ignore. In my adolescence, I remember reading one of these biographies and thinking that if she could immigrate to another country and stave off death to study science, I could stick out intro to physics. Many biographers of women scientists treat her as the first and most inspiring female role model of the modern era. And I too introduce her first in the stories that follow, but not for the same purpose. No doubt her work helps to make the case that science is made to be manly rather than being inherently so. But Curie's myth haunts these pages and the psyches of succeeding generations of women more completely than her real life example, for it has both empowered and stigmatized women, liberated and constrained them, often at the same time. The historian Margaret Rossiter noted an inferiority complex in women after Curie's tours of the United States in the 1920s, and for generations, the Curie complex has continued to allow men to disqualify women and women to disqualify themselves from science. Women scientists have felt as though they cannot measure up to Curie, and of course, how could they, when this mythical measure of female competence has morphed in the American mind over and over again? It's like trying to hit a moving target. I have organized my stories of women around 3 historical hubs that coincide roughly with the first, middle, and final third of the 20th century. So we've been talking a lot about 20th century physics, for example. We just finished a book as a reference for that. And then that led us to other topics such as dark matter, which we talked about just now, earlier on in this live. This will be another way to kind of recap the 20th century, actually. As we talk about these women scientists in this book, we will also take another look at the main highlights of the 20th century and the developments that happened at that time. And actually, you'll note that when we talked about Einstein's cosmos and how Michio Kaku talks about the 20th century, he does not really talk about women scientists' role too much at all. It's hardly mentioned. So hopefully this book will kind of correct that and we'll get the full picture. The first is characterized by scientific professionalization, the second by World War II and the post-war veneration of masculine science, and the third by the rise of second-wave feminism. Regardless of the historical backdrop, the stories contained herein speak to questions about women in science that continue to be relevant in the 21st century. Can women be both womanly and scientific? How do women balance their home life and scientific careers? How do men and women collaborate in the lab? Are certain scientific environments better for women than others? Do women do science differently from men? Is there such a thing as feminist science? Oh God, rarely did the women in these pages ask such questions explicitly, and yet their stories make us reflective about possible responses. In part 1, assistants, housekeepers, and the interchangeable parts, the masculinizing effects of professionalization redefine women's relationship to science in ways that reverberate today. The very definition of professional science relies on its antithetical concept, amateur science, defined in its methods and orientation as quintessentially domestic. In professional settings, women performed science in relative obscurity or occupied niches in pedagogy, popularization, and domestic research. When they made inroads into men's labs, it was almost always as assistants, technicians, and helpmeets. In Chapter 1, Mary Curie found herself negotiating American expectations of womanhood when she toured the United States to obtain radium for her research in the 1920s. Hi, Key! Thank you for reading and explaining also. This is the hidden history of women in science is interesting. Yes, thank you. I thought I will share with you. I will watch the rest after you upload. Okay, now must go to lab to take blood test. The flag is Brazil. That's what I was thinking, but I didn't want to guess it wrong. Thank you. The flag is Brazil. Thank you. Welcome to Brazil. Thank you for being here. You have to take a blood test and also foot care. Okay. Good luck. Hope everything is fantastic. Take care. Good morning to you. Good luck. I hope everything is okay. So Mary Curie was touring United States to obtain radium for her research in the 1920s. Her admirers could not idolize her as a scientist, except to assume that domesticity and maternal benevolence motivated her work. In the American press, she did not discover radium for the sake of science, but rather to minister to victims of cancer as good women would. In Chapter 2, Missy Melanie, the American journalist who organized Curie's radium tours, asked the Nobel Prize winner to nominate the industrial engineer Lillian Gilbreth for a Nobel Prize in 1932. Curie told Melanie that she would oblige if she knew which Nobel Prize to nominate her for Gilbreth was not a chemist, physicist, or medical scientist. Indeed, throughout her life, Gilbreth defied the facile categories of others. She was mother and wife and hence a domestic woman, and yet she also made a living in the most virile of scientific fields. Male industrial engineers sometimes ignored her, if not her work, and yet she became one of the most popularly recognized American women of the 20th century. What makes her story emblematic of so many other women scientists is that few of her admirers recognized her as a scientist at all. Women scientists in these years often went by other names, whether they liked it or not. Baji, good night. Good night. Women scientists. In Chapter 3, for example, the first generations of women computers meaning they were actual people at the Harvard Astronomical Observatory, suffered similar sexist semantics. Though they worked in university buildings where serious research presumably took place, they were tolerated as scientific housekeepers, custodians of records, cleaners of equipment, boosters of morale for the important men in their presence. Records viewed today amply demonstrate that the work of the Harvard computers was often more interpretive and groundbreaking than its categorization as busy or domestic suggested. Still, Annie Cannon's embracing of her status as a womanly helpmeet to male astronomers won accolades for her, as well as the ability to establish funding for women in future pursuits of science. When we examine the career path of her younger co-worker Cecilia Payne Gapushkin, we see advantages and drawbacks to both assimilation in masculine professional culture and capitulation to traditionally female positions in science. In this instance, history complicates as much as it clarifies. Wow. Okay, we're almost done with this first little chapter here. I need to take a few sips of my drink. It's getting very, very cold. Give me 1 second. Actually, I need to charge my phone too. let me charge it for 1 second here. Then we will continue. Thank you, everybody. It's an interesting book here. Chapter 3, we will talk about women computers. The cult of masculinity in the age of heroic science. Assistants, housekeepers, and interchangeable parts. Women scientists and professionalization, 1880 to 1940. Wow. This is gonna be depressing, isn't it? This is gonna be depressing. A little depressing right here. A little bit depressing, I must say, this book. We're talking about Madame Curie complex. Hi, Baji. Up this up. It's what I do at late nights these days. They did a presentation. I okay. Hi, Baji. Here is Shona. Mama's here, baby. Don't you worry. Don't you worry. Mama's here. Here, Baji. Come, Baji. Tinta থেকে presentation. Baji. Oh my god, Baji, your nails hurt. It hurts, Baji, it hurts. Baji sitting on my lap with his nails out. Hi, baby. Baji Baba. Baji is a goody boy, goody boy, goody boy. Baji is a goody boy, goody boy, goody boy. Baji, তুমি ভালো ছেলে? তুমি good boy. তুমি good boy. Hi, তুমি good boy. Such a good boy. কত ছোট, কত ছোট ছেলে তুমি, কত ছোট ছেলে, কত ভালো। একটা ভালো ছোট ছেলে কাকে বলে? বাজিকে বলে। বাজিকে বলে। বাজিকে বলে ভালো, আর বাজিকে বলে ছোট। ভীষণ ছোট তো, ভীষণ ছোট। আচ্ছা তুমি কি কচু ছেলে বাজি? তুমি কি কচু? বাজি তুমি কি কচু? তুমি কি কচু? Baji, your nails are hurting. Can you please make biscuits without claws on? Baji is making biscuit but with claws out. Biscuit Baji. Baji तुमके biscuit. Aww. Baji কত কোম্পানি দিচ্ছে আমায়, কত ভালো ছেলে। তুমি ভালো, তুমি ভালো ছেলে। almost done. Oh shoot, you know what? What day is it today? November 27th. Hey, Reese. How are you? Me too. Why are you feeling a bit crap? Must be one of those doom days. What do you mean? Let me get my phone and then you can see Baji on my lap as well. I was reading this book, Madame Curie Complex. A little bit left in that first chapter. I get that. I've had that too. I can also feel a bit anxious and panicky sometimes. I sleep with a sound machine, and I mean, today was not too bad. I was feeling good, but I don't know, you know. Just life. It's feeling. Yeah, I don't know. I think today was mostly a good day though. It's been good, but it can sometimes be a little bit bad as well. In waves. So anyways, let me finish let me finish this chapter. Doom waves. Yeah, something like that. So there's very little left here for this particular chapter, so I'll finish it off. It's kind of introducing this book, Madame Curie Complex, and talks about the role of women in science and also kind of the types of things that they may have. Oh, hi. Hi, Four. How are you? So, part two, the cult of masculinity in the age of heroic science, addressing the period of the middle third of the century, describes a time when science enjoyed its highest esteem in American life, as well as its most virile identity. While Albert Einstein was a popularly recognized figure in the 1920s and 1930s. Yes, that's right. While Albert Einstein was a popularly recognized figure in the 1920s and 1930s, during and after World War II, when the ramifications of atomic science became widely apparent, the image of the male physicist became still more venerated. Robert Oppenheimer and Enrico Fermi became larger than life in the American mind, revered in ways no woman scientist has been in the post war era. In Chapter 4, cultural amnesia regarding women of the Manhattan Project is seen as one consequence of the masculine mythology of these years. Another is the devaluation of women's noble caliber science. Chapter 5 illuminates how Gertie Corey and Maria Gippert-Meyer benefited from their close proximity to scientific men and were acknowledged as noble-worthy scientists, and yet being married to prominent men also meant tolerating decades of underemployment. They treaded close enough to men to be supported and protected while keeping an arm's distance to also to be distinguishable in their own right. The Nobel's snubs of single women, Lise Meitner. Oh my gosh, we talked about Lise slash Lise. I don't know exactly how to say her name. Lise Meitner and Rosalind Franklin. As far as Rosalind Franklin goes, and the fact that we did not give her a Nobel Prize, that's like freaking beyond me. That's probably the one I'm most pissed about. But yeah, they did not get it. Represent more cautionary tales, but the qualified success of Nobel winner Rosalind Yallo, treated in Chapter 6, suggests that succeeding in institutional science in the post war years required a crafty adaptation of the masculine role for legitimacy and the womanly role for acceptance. Part 3, American Women in Science in Transition, covers scientists during the last third of the 20th century. With the rise of second wave feminism in this period, professional science began to shed its masculine trappings, at least in the work of Louis Leakey's Lady Trimates, Jane Goodall, Diane Fossey, and Berit Galdikas. In chapters 6 and 7, I relate how Barbara McClintock, Rachel Carson, and others seized on and facilitated this moment of flux. They rejected man's presumed dominance over nature as well as beliefs in masculine objectivity, to embrace scientific work as popularizers, naturalists, and advocates, bearing willingly, even boldly, labels that had been long placed on women so as to reduce them to scientific amateurs, quote unquote. Baji's right there. In this post atomic age, both male and female scientists have come to understand the importance of bringing non scientists into their work. For decisions about nuclear bombs and gene replication have social ramifications that cannot remain secret. Women's ability to make science accessible takes on new significance going into the 21st century. I concede that my pigeonholing women scientists into tidy historical categories of which they themselves were never aware may be fraught with problems, but I trust that this volume makes clear that I want not to reduce women, but rather to position them to see anew, perhaps even for the first time. I hate all the men versus women stuff. I also want to create a useful framework through which to see many facets of gender in science. Several women practiced science across my sometimes arbitrary chronological divisions, and certainly women's lives and thoughts transgress the generalizations I've made about them as members of generational, disciplinary, or ideological cohorts. Still, there is a larger picture that the individual stories of women can clarify when the narratives are put together and seen as a whole. Suddenly, the history lens changes too, and we can see women practicing science when it wasn't in the lab, the university, or under Stag Field. We can even flesh out the one woman who did stand witness to the nuclear reaction my father talked so much about. Her name was Leona Woods Marshall, later Leona Marshall Libby. In this volume, she's more than a footnote. She's a fresh pair of eyes on the culture of American science. So that's what the introduction to the book is. I just kind of went through that. Once again, this is Madame Curie Complex, Hidden History of Women in Science by Julie Desjardins. It's a shame how men used to treat women. The divide exists even today. Yeah. Oh, yes. Because a lot of prominent men, in my experience, in my own personal experience, working with a lot of male colleagues who have, many of them have been also a big pleasure to work with and have mentored me, etc., etc. But I think, it's definitely the case that a lot of prominent men in science and other fields basically are married to women who are, they're like stay-at-home partners. So they're not really used to women in their own lives kind of being also in the professional world. That's one view of mine. So I don't know. I think it does make it difficult to be like the one woman colleague of all these men, or one of the few women colleagues of all these men. So that was my own personal experience, at least, whatever. The year was 1921. So we're starting this chapter now, the first part now. The year was 1921. So it's going to be very interesting. This is a book written by a woman. It talks about women in science and sort of a historical view of it, and Madame Curie complex, and brings into view a lot of different aspects that we might not ever read about or learn about from a more male perspective, that is. We just covered 20th century physics from a very male perspective in the sense of the book we were referencing, Einstein's Cosmos by Michio Kaku. And, there was very little mention of any women doing anything scientific in that book, as you noted. In just a couple of sentences, he mentioned Lise Meitner, who basically did something extremely important. There were a lot of other women as well, around these times, as well as pretty much probably the whole time. that we just haven't met very much, or they're kind of more hidden. Even somebody as famous as Mary Curie, how much do we really know about her versus what we know about Einstein, for example. So I think this book kind of treats all of this and gives us a very different view. And I think it'll be a good revision or review, because we just talked about the 20th century physics. So we will kind of get a review of that, but from a different perspective in this particular book. So it'll be nice. I kind of like the 20th century. So in that sense, we'll kind of have another perspective on that. The year was 1921. The physicist Robert Millikan announced that the nation's expanding technostructure required better selection and development of men of outstanding ability in science. His call for men was not accidental. He imagined the best candidates to be masculine, rugged types and likened them to explorers in search of nature's gold. Thomas Alva Edison, holder of more than 1,000 American patents and the most widely recognized scientist in the country, embodied this enterprising pioneer as he attempted to recruit young men in his mold to develop technologies in his research facility in West Orange, New Jersey. Edison would not settle for small-time thinkers. His term of A-class men would be drawn from applicants who passed a rigorous test he had devised, but his recruitment of efforts proved disappointing. Of the 500 men who applied for positions, only 6% passed his exam. His own son failed to earn a place in his ranks of A-class men. Test takers grew defensive. They were not common street folk, but graduates of science programs in the most prestigious universities in the country. The problem lay not with them, they claimed, but rather with Edison's arbitrary criteria for gauging scientific competence in the modern age. Some of the questions on his exam were what they were used to. What pinch pressure at the driving wheels does a 23-ton locomotive require when drawing a load of 100 tons on level track? That's a question for you, Reese. Yeah. Not a fan of Edison, I must say. Yep. Well. Yeah. Others, however, seemed highly irregular for testing scientific competence. Who was Leonides? What is the name of a famous violin matter? What is felt? One stumped job applicant wondered how many $10,000 per annum men could have answered 50% of this tomfoolerism. Another dismissed the test as vulgar and an insult to his educated sensibility. Who cares, he wrote. Who cares who wrote Home Sweet Home? A college graduate lashed out. We are in an age of specialization, and men are being trained to do things in certain lines of work that do not allow them to waste time and gray matter on general knowledge that can be had by referring to an encyclopedia. Not all reactions to Edison's questions were defensive. Some thought that the test proved just how amazingly ignorant college men had become. I think that any man who cannot give a prompt answer to 75% of the questions at least is lacking in education, and if a college man had wasted his time in college, asserted an anonymous reader of the New York Times. Another reader thought that the questions answerable by any well-read and average intelligent man or woman, regardless of college credentials. Some thought it refreshing that Edison looked for men who didn't have one-track minds. Gosh, so much about men. Who sought to expand their mental storerooms rather than let them atrophy. A doctor from New York believed that more test takers would have passed had they devoted time to book reading than ball games, moving pictures, the sporting news, and other preoccupations of American males. Readers who followed the story flexed their cerebral muscles by taking the exam themselves. Men congregated in subways, clubrooms, college dorms, and hotel lobbies, jotting down answers to questions they speculated had been on the exam. People were wholly invested in establishing whether or not the exam tested scientific competence, and those with and without college training were curious about how they would perform on it if it did. And as erudite as Edison appeared through all this, people seemed to forget that he had become who he was without the assistance of professional degrees of any kind. He never went to college. As a boy, he was homeschooled and thrown quickly into business ventures to fend for himself. He observed the world around him and learned through reading and hands on experimentation. As an established inventor, he still boasted a subscription list of 62 periodicals, most of them scientific but also economic and legal, and others oddly eclectic. Science and technology fascinated him, but so did geography, literature, and music, realms of knowledge that academic specialists considered generalized trivia in the technological age. Edison's hands on experience of science reinforced his opinion that academic specialization, the hallmark of the modern university, had stifled human curiosity and compartmentalized men's thoughts until they knew lots about minutiae and nothing about anything else. He doubted that a modern college man could come close to filing a patent portfolio as large and varied as his, for it was unlikely that he was as inquisitive about the natural world. He put college men on the defensive at a time when they had sought authoritative status as experts. His exam had burst open a pregnant debate about college versus practical industrial training, but it also brought to the surface questions about the intellectual equipment of educated American men. In determining that his applicants were ill equipped to handle modern day problems, Edison had essentially emasculated them. Women observed these debates from the periphery and had their own opinions. It is the men to whom we are accustomed to look for intellectual guidance who said the test could only be met by an encyclopedic mind, reflected Ellen Lynch of New York. She thought it a matter of unsentimental fact that there was not a question in the list that could not be answered correctly by any well-trained boy or girl of 16. Who are the real best and brightest? Another woman posited. Masters of some atomized niche, or broad thinkers with the capacity to draw knowledge from many parts of the social and natural world. Female readers of the Times seemed to relish the opportunity to respond sanctimoniously to these questions. Edison's test may have been of deeper significance to them than their husbands and fathers supposed, for it challenged the assumption that academic channels open almost only to men were requisites to a scientific mind. Perhaps women's hands-on study of nature, unpaid, without title, without resources, and outside of university, was of value. After all, for a long time, women had been told otherwise. Wow. Goodness! Look at that. What an effect it had on women. Wow. Oh my gosh. I'm so sad. Most women at that time, I guess, did not really go to university. They didn't have women getting educated as much. Wow. Education really is a privilege. The notion that women and science didn't mix had deep roots, traceable to Aristotelian and Platonic ideas about nature and knowing and enlightenment views that supposed men and women's inherent traits to be complementary and oppositional. The Greeks linked femaleness with passive, indeterminate matter and maleness with active, determinate forms, and in later generations, the observation of fertilization under microscopes interpreted as a motile sperm penetrating a passive egg seemed affirmation. Eventually, Kant, Rousseau, and other liberal philosophers, male by definition in this tradition, insisted that women were anti-intellectual by anatomy and default. They were lovers and feelers, men thinkers and doers. Early positivists such as Newton, Descartes, and Locke also conceptualized links between external, interestedness and male knowing, and internal subjectivity and female knowing. They grew confident that, that nature was knowable through the senses or experiment, but only men, not women, were equipped to unlock its mysteries. Philosophers from Bacon to Goethe, I don't know how to say that. I've seen it before, I just don't know how to say it. Nietzsche all assumed that the prerogative of rational man was dominance over female nature. The mastery of nature and woman was essentially one and the same. Oh my gosh. Well, how sad. We will be reading this book only a little bit, not like fully. I don't want to depress myself. But it's interesting though. It's interesting. Look at all the highlights I made. This was part of a class I took, and look at, wow, I've read a lot of this back in the past. In the past, indeed. Hi, Baji. As the ideas of scientific revolution took hold, they fostered the rise of industrial capitalism, which in turn privatized family households. Poor and working class women and men went to work in factories, though among the burgeoning industrial middle class, the divisions of labor and spheres of influence were more clearly distinguishable between the sexes. Ideal men occupied the public realms of learning, politics, paid work, and eventually professional science, while ideal women occupied the supposedly subjective and sentimental domestic sphere. Women were said to excel in such activities as cooking, cleaning, nurturing, and soothing daily quarrels. What? Good science, as mirrored in the male professional, however, required unemotional and empirical thinking in abstract and universal terms. Whether or not individual women or men possessed traits to support such binary views was irrelevant, for cultural stereotypes possessed logic of their own. In the 18th century, a knowledge of natural history had become part of the intellectual equipment of well-to-do women, and it continued to be a popular subject of the Lyceum circuit through the 19th century. Botany, in particular, had long been cast as an avocation of women with leisure and means sufficient to cultivate herb gardens and collect specimens for men to analyze. Hi, Baji. Editors of such domestic periodicals as Godey's and the Ladies' Repository encouraged women to attend public lectures that would help them to nurture their children's love of plants, assuming that women readers were sentimentally drawn to the care of living things. Ah, Jane Marcet was among the women who wrote best-selling science books in the 19th century. In the 19th century, astonishingly in the field of chemistry, not botany. Her success can be ascribed to the appropriately pedagogical tone and style of work, often organized as conversations between mother and child. Oh my God, wow. Well. Hi, Baji baby. Hola, Baba. Hi. Ah. We're sleepy. I think we have to finish the live, or we have to go live again tomorrow. We're sleepy. Are we gonna go to bed, Baji? Yes, we are. Thank you, everybody, for joining. We started this book, Madame Curie Complex. We will continue this discussion, as well as more about dark matter next time. Thank you for being here. Baji says good night. Baji says good night. Good night. How are you feeling now, Reese? Feeling better? I hope you feel better. Thank you. I think there has been a bit of an existential crisis. That's what it was. I started to feel an existential crisis this week. Are you feeling better now, Reese? Okay. Yes, I'm sure. Oh, hi, hello. Look at Baji. Baji wants to eat me. I'm sorry, Baji. I'm sorry I disturbed you. I'm sorry I disturbed you. I'm sorry. I'm sorry. Come, Baji. Well, Reese, leave us a comment on our videos. Give us an update later how you're doing. And thank you everybody for being here. Sleep well, Andre. Okay. All right. Bye. Bye bye. Good night.